Okay, hello to people joining this live stream. We are going to be talking about multi-computation and support for that in Wolfram language. And for everybody, let's introduce what it is that we are talking about. Basic point is, what normally when we do a computation, an evaluation, we have a definite evaluation sequence. And several things are true about that evaluation sequence. First of all, there's only one thread of evaluation. Second of all, you're just evaluating things and getting, well, okay, so what is special? Maybe we should start off by characterizing that. I think I'm going to put this in here again for now. Current evaluation scheme. Special. What special features does it have? It is, one special feature it has is that it is primarily oriented towards input goes to output. That is, it is not dealing with, no infinite computations. It's only a finite computation where we're giving, so that's one thing. Another thing is that it is a, single thread of evaluation. And that's, picking a particular evaluation sequence. And another thing is, it is an answers only scheme. That is, there's no tracing of what happened in the computation. Okay, so now what we're interested in is generalizing all three of those things, and maybe there's more. Am I missing something that we're special right now?
No, I don't think so.
So, I mean, the objectives are to deal with multiple threads of evaluation. That's the whole multi-way system idea. To deal with computations that might be infinite and where we're sampling things from the infinite computation, and which is, closely related to, well, and also things where we trace more about what happens than we do now. So, for example, where we have causal information about what had an effect on what, and so on. So does this seem, and the goal is to have a small number of functions that can support all of this. And we've looked at this a little bit before. Okay, so actually, related items. Related items include traversal order for traversal order, which right now is something in trees. We've defined for trees. What about map, for example? What about map? What about evaluation in general? And the key issue there is the key issue is we've got two forms of recursion that we're doing right now. We are doing expression recursion, and we're doing reevaluation recursion. Does that make sense to people? That is, and what I mean by that is that we're both recursing through. We're deciding which place in the expression do we do something at, and then once we've done something, we're deciding of the things that we just reevaluated, which one do we pick up first. So, for example, here, this would be. I mean, this is a example of a representation there of Fibonacci, right? And where what we are, in our model, we're doing depth first recursion. In our standard evaluator, we are doing, in this case, there isn't much expression recursion, is there? No, there is some, because there's the 5, f of 5 plus f of 6. And we have to recurse into that, looking at the f of 5 first and the f of 6 first, and so on. Okay, so that's one thing that's related. So another thing related is, find shortest path. The dynamic version of find shortest path, aka the thing I've written and other people have written, find replace path. That is, what one might call virtual path finding. And what I mean by that is, if you have an explicit graph that's sitting in front of you and you want to find a path in it, that's one thing. But virtual pathfinding is you didn't actually construct the whole graph, but you want to find something from that. And that is related also to find equational proof, etc. And for example, stuff that we've been doing for this metamathematics project has, we've really turned, so find equational proof is almost like sort of virtual pathfinding in a multi-way system, although it works in a slightly different way at the end because of this resolution theorem proving idea.
Yeah.
Just making it so I mean, for example, we could say, to give an example of this, we could say find equational proof of what's a good example? We could do, let's do something not super complicated. Well, the only one I ever remember is this one. Actually, let's just for fun, I'm just going to use, because I think it might, let's just see whether that does anything different. Oh my gosh, that was only 76 steps. Okay, so then now we say proof object to token event graph. Okay. Well, that was a little hard to read, but this is showing, Roger, for example, do you understand what this is?
Yeah, I think so. Can
Okay.
you highlight what those rings are? They probably tell what you use to get to the next step, right?
Exactly. So this is a substitution step. This is what Nick and we are calling by substitution, which is sometimes related to what in theorem proving community is sometimes called paramodulation, or it's a generalized. So one of the issues here that's coming up for this is the notion of two-way patterns. That's a related concept here. But so this is an example of virtual pathfinding, right? That is, there's a graph from the theorem proving, there's a graph that the axiom system implies, but we're not finding all of it. We're just finding this virtual path. Let's see. Oh, I was about to write something else down here. Well, anyway, okay, in tree traversal order, I want to remind people we just introduced with named traversal orders, right? And, okay, so another related item is the long time and very unsuccessful trace function, which was an attempt to do this thing here, no tracing of what happened, right? It was an attempt to say what actually, because like things like replace, I suppose it's also related to the things we were talking about yesterday, which is this position applied and etc. That is when where when you're using map, for example, we have map index, but you could say something like map position applied of f comma, and then this would also pull in as a second argument to the thing that you're feeding into f. It would pull in the position. Okay, and that's all right. So anyway, those are some related things. Is there anything else that's obviously related that I should have? Oh, another thing that's related is probabilistic programming and Monte Carlo. And Roger, what do you think? I mean, what are things related to that you think might be relevant here?
Well, something that looks similar to this is that you can do basically random path sampling, in a probabilistic programming in Monte Carlo.
Okay. Right. I mean, chemical reaction networks, that's another use case we have here. Okay, so we've also got sort of examples that we've done so far, of which the combinators work is one example where, this has been studied decently. The metamathematics thing is another example where we're studying this in some detail and really making use of all of these things. I've also got these things like this, multicomputation with numbers, where I looked at this. Anyway, so that's a bit of an introduction. What are we trying to achieve? Oh, here we've also got some comments. Right. Oh yeah, another one I wanted to mention was beam search is another example of a type of thing which is sort of related to this. That comes into the virtual pathfinding area, I believe. Okay, so what is our objective with all of this? The objective, and also, sorry, we should also have mentioned, logic programming is related to all of this, etc. The objective is small number of powerful functions that just do this. So Nick has a function here, which apparently does a bunch of this. Actually, functions we have. So one thing we have is which is unfortunately way too super of a function, is multi-way system. What is multi-way aggregation system? Why is that even in there? Do we really have that?
Last time I looked, like during the summer school, I think they had like there's multi-way system, and then there's like 5 other multi-way CA, multi-way aggregation system, multi-way, etc. functions. I'm not sure which one is like the newer one. I think the single multi-way function is.
Well, I didn't even remember that. Yes, yeah, I think that look, the multi-way function. I didn't remember we had this at all. My gosh. Okay, where do we have this?
Yeah, there are a bunch of.
I mean, do we think concurrent programming in the core language is part of what we want to achieve?
Yes, because eventually, the first thing we're going to do is just implement this sequentially. But the goal ultimately would be to have something where this could actually be where we have a clean enough formalism that through the compiler and so on, we can actually do things genuinely in parallel. And being able to do that is very dependent, I think, on what am I trying to say? On having the cleanest possible formalism, because the pi calculuses of this world and so on are just too complicated. We don't care. People don't understand them. This is okay. So let's see. We also, I don't know what the relationship. I mean, Petri nets are another related thing here, and we've got all the non-deterministic Turing machines and so on. So we've got, okay, what are we going to look at here? There's a lot of multi-way things here. Okay, probably the main one is multi-way system. So just to give a sense of what's here. Okay, so multi-way system, there's like, what system are you operating on? And there are a few we've supported here. And in the end, we have this notion of state evolution function, state equivalence function. So the equivalence function has to do with when do you merge branches. The state event function has to do with what are the events that will be causally connected to other events. Right, so this is sort of a decomposition of what we're thinking about in terms of the different pieces. Oh, by the way, another thing we should list here is breadth first search, which is a function which I consider to be way too complicated. I mean, I've essentially never used it because this is, breadth first scan rather. Right. So the problem with breadth, who here has used breadth first scan?
I think I've used it once.
I think they're both depth first scan and breadth first scan are too complicated. I agree.
Right,
I've used a very limited subset of its capabilities.
Sorry? I mean, they're too general. I think that you.
I think I think it's the same issue as a multi-way system. I think they have the same design problem, basically. Because I think this whole thing about, this is very similar to the problem of evaluation fronts and so on, I think.
It is.
And how
but
does
I think most people don't need this level of generality.
Well, I agree, but I think it's a packaging. Yeah, I think it's bad, but we all agree it's bad packaging. But Ian, how does this relate to tree traversal order?
So there's two separate functions for graph that give breadth first and depth first. But in tree traversal order, it's just an option for tree map.
And how much do you cover for trees what breadth first scan? So breadth first scan is for a general graph.
Yes.
How much of this already shows up for trees and how much of it is specific to graphs? I mean, how much of it, I mean, how much of all this stuff could you, how general are graphs?
Well, I think
how
the
general
thing
are trees, rather.
with these is that it has like a distinction between visitation and discovery and the potential of things being rediscovered and revisited.
Okay.
And I think neither of those distinctions are relevant for trees.
I see. Has discovery plus visiting. Okay, so because you're saying in a tree, by the time you're
that
there,
and potentially revisiting.
Yeah, I mean, in a tree, it's you go through it once.
Right.
I don't know whether somebody wants to comment from a physics project point of view. I think that when you don't, if you have a post set and you don't have a closed time-like curve, I don't think you do revisiting. In other words, if there's a partial order, there's no revisiting. Is that true?
Yes, that's a DAG. So
right. Okay. So by the way, this reminds me of two other things which should be here, which is, we don't have a DAG data structure, do we? Do we have that?
You mean of the actual data structures, or do you mean just anywhere? I mean, we have graphs. I mean, like their functions like. I mean, their functions like what topological sort basically takes a DAG, right, and it just takes it as a graph.
yes,
I don't even know what does topological sort do.
it's a linear order compatible with a partial order.
Wow. I had no idea we even had this. What is it? I mean, oh, I see. It is a particular ordering.
Yes.
So, in other words, topological sort should have, I see, topological sort, in a sense, should be the thing that is fed, this effectively should have lots of evaluation order control.
One could.
I mean, or this, in fact, is the quintessential foliation control, foliation. Let me show you one other thing, which is, I mean, that's a place where one could, if we had a method of describing foliations, reference frames, orderings, this would be a place it should be fed into. Let me show you something which I've probably shown.
But by the way, though, I mean, about having a DAG data structure, I mean, I think that I don't think that would really make much sense, because I mean, the only reason we have trees is because trees are like really different from graphs, and like the applications are really different.
Okay.
Right. But I think DAGs, there's a lot more overlap with graphs.
I don't know.
And, we don't want to have, I feel like it's one of these things we don't want to have, there's graph and there's tree and there's DAG and there's directed graph and there's undirected graph and there's, blah, blah, blah.
What about in the data structures area? I mean, does it make any sense there? There must be.
Well, I think that for data structures, I mean, I feel like for it to be consistent, there has to be an actual like data structure that's like, here's an efficient way of representing a DAG. And I'm not sure such a thing. I mean, there probably is some efficient way of doing it, but like, I'm not sure there's a standard data structure for that.
I mean, internal uses of DAGs is pretty extensive, of course, in the implementing the system.
Well, but that's a good reason to expose it in the data structure project. I mean, so Roger, when we're implementing DAGs, is there one representation or are there many representations?
Many. So you implemented, probably, maybe even you yourself, for expressions, where we basically reuse pointers.
Yes.
Share, wherever,
Yes.
Okay. So there's one. What do you use a data structure that's compatible with everybody else's? I doubt it. I think it's like some custom thing in there, probably.
Yes.
BDDs, which is a way to implement Boolean functions, completely relies on a very efficient DAG structure.
Right. What do we do? So
But that is its own thing. There's a lot of things that go into sort of getting efficiency in that structure that cannot, and it's not exposed either.
it's not exposed at all. So because we can convert to BDDs, can't we?
Yeah.
But what does it even mean? How do we give the output as a BDD?
No, we got a Boolean function. We don't have BDDs. We have Boolean function. And so Boolean function is free to use other representations too, right? Because it's an abstract representation, as long as it performs what a Boolean function should perform.
I didn't know it could have stuff inside it that isn't just a straight table. So you're telling me that
No, a straight table is like no. It's a table for Boolean functions. It's like that's maybe 50 years ago or something, but no, that's not what.
I mean, like if you have a 25 input Boolean function, it better not have a table in it.
No, right.
Well, fair enough, but then so what is a Boolean decision tree and how do we represent that? So if I say, for example, Boolean function.
Well, hold on. Doesn't Boolean convert? It always returns some sort of. It always just returns like a Boolean expression, doesn't it? Like it returns just like ands and ors and stuff, or Boolean.
This thing gave you a bunch of other potential outputs.
Right, but so this is if I say Boolean decision tree. Is that just a representation like a is that like a DNF or something, or is that if I say expression tree of this?
Yeah.
Oh, is that deeper than a?
Yes.
Yeah, because it's a Boolean decision tree and not some disjunctive conjunctive normal form.
I didn't know we could do these. How long have we been able to do these?
Well, look at when the date it was introduced. 2008.
But so what can it do then? I mean, how good is it at doing multi-level logic optimization?
Well, it's very good. Depends on what your goal is, but it's optimal. So given a variable ordering, you can compute the optimal DAG to represent it. So another way to see a BDD is that you use common sub-expression elimination. And so you give names to those subtrees, and that's why you get the DAG instead of a tree, right? You give names to those. And given that ordering, we always compute the optimal one. So that's the absolutely minimal DAG.
So,
but here's the thing to remember. With n variables, there are n factorial possible orderings.
Yes.
So if you change the ordering, you might get something that's dramatically smaller or bigger.
Okay. But so, for example, if I go ahead.
Out of curiosity, right now it's generating this minimal DAG using what ands, ors, and nots. Is there some way, of getting it to use other, other connectives? Or does the algorithm even work if you use other connectives?
Well, BDD is defined in terms of ands and ors and not. There's something called BMDs that I kind of worked on before, which is basically using XOR and ands. And in some cases, like for instance, if you want to verify an arithmetic logic unit of a microprocessor, that's a lot of variables, right? 64-bit in for each of the variables in and 128 out, and so it's about 200 variables easily to represent that thing. So, but also it's proven that a multiplier, there is no possible way to give an efficient BMD representation of a multiplier. But there is a very efficient BMD representation that uses basically XOR, which is mod 2, multiplication.
But like, I'm just wondering, are the algorithms
Or
that do this, are they like pretty much like the fact that it uses XOR and is like super hard coded into the way it works?
Yes,
Or-
it is. Yes,
Okay,
it
yeah.
is.
But so the one that we have is using and OR. Is that correct?
Yeah.
But we could have one that used different functions.
Yeah.
I don't think I've ever seen this before. Those would claim to be the minimum and or arbitrary depth trees. Is that correct?
For that variable order, yeah.
Huh. Wow. Didn't know that was possible. All right. Well, learn something new every day. I do. I learn.
I mean, no. The depth is always the same. So the depth is always the number of variables, and you don't count not as a level. You don't. No, the convention is that you don't treat not as a thing.
Mm-hmm.
Okay, so then there are sort of n variables. The depth is always n.
Why? Why can't you reuse the variables? I mean, these things seem to have. So
that's our expressions.
Right. So the point is underlying if there was an option for expression graph, so that basically identical sub-expressions got merged, then those would become DAGs.
Yes.
Right. So the DAGs were expanded out into trees because you can't have an expression that on the top level looks like a DAG.
That,
so
but
that
also,
yeah, go ahead.
But also the thing is like not is treated as a if you look at the tree, that these seem to add a level.
Yes. Okay.
And it depends on how you define what abstraction you use for a tree or a DAG, right? Is that a level or isn't it?
Okay, let's come back over here to, I was looking at, in this case, this is,
and by the way, when we say two-level Boolean minimization, we don't count not as a level.
Yes.
Only and or.
Right. Okay, so here, this is basically foliationology. Okay, reminder. So this is, this is defining a partial order. And then
I'm thinking of foliage when you say that, like green trees and stuff.
No, what we're talking about here is anti-chains and posetsets. Okay, we're talking about ways in which you can define slices where you eventually visit every node. See, this is a total order, right? But you can also just say which of these things can be simultaneous, so to speak. Does that make sense?
Yeah.
Right. So here, these can be simultaneous because they're not time-like connected.
Mm-hmm.
And this is an enumeration of possible total orders. Notably, our tree traversal order certainly doesn't cover all of this because we're only naming particular tree traversal orders. So the question is, what's the sort of general case of how do you specify a useful traversal order? Does that make sense? I mean, clearly you can give a traversal order by just saying visit nodes 1, 7, 5, 8, 4, and so on. But if I was going to go further down in this, I would like something which is a general formalism for how to specify traversal orders. Anybody know any approach to doing this? I mean,
what it also reminds me of is out of order. So for instance, and sometimes you don't want the complete order, you just want the partial order.
Mm-hmm.
But I mean a total order, but the partial order. So for instance, in Grosvenor bases, there are these exponent vectors. They look kind of like your thing there,
mm-hmm.
In 2D. And the question is, what order do you visit those exponent vectors? And that needs to be a total order. And it needs to be compatible with the way you multiply monomials, so which is vector addition, basically.
But that is relevant for, I mean, that's the same thing as the Knuth-Bendix question.
Yes. I mean, yeah.
Which is the same thing.
Grosvenor basis is Knuth-Bendix And Grosvenor basis is one and the same algorithm at some level.
Yes, but I mean the issue, the issue here. This is also related to the theorem proving question.
Because that is Knuth-Bendix, right? It's an unfailing Knuth-Bendix.
Right. Okay. All right. I mean, what's interesting about this at a meta level is how many things that we care about are sort of the same problem showing up in different forms. But I did want to mention here, wherever it was, multi-way system, okay? The huge mess of different things that you can generate from the multi-way system. So look at all that stuff, which includes things like Knuth-Bendix completion rules and things. And, you know, part of our goal here is to clean all this up. And just for people who are not involved with this, the tour of basic things that we have here. God, there's so much stuff. I mean, there's some, yeah, I mean, so. Okay, so multi-way system of, let's say, a string multi-way system.
I mean, one thing that's interesting in all these cases is to be, in some ways, efficient.
Yes.
So, you know, like there are many ways to compute Grosvenor basis. There are many ways to do Knuth-Bendix completion, and some things are dramatically more efficient than other ways.
Right.
But the thing is that, you know, like with naive search, you can't try them all. Like you know, like I said, the BDD, there are n factorial orders. For Grosvenor basis, there are n factorial variable orders, but then there's a whole tower of additional types of orders you can have on top of that.
Right.
And I assume similar things happen in equational theorem proving. You know, it is, you know, so what can you afford to do? It has to basically be heuristic. It cannot exhaustively try things. So
I know, but you are talking about the old paradigm for computation, where basically you want one answer. And I agree, there are a lot of things which are naturally stated multi-computationally, but where the thing you want out is one answer, like one path, basically.
But you want the efficient one. You don't want the slow.
Oh, absolutely. Yes. I mean, that's where I was talking about this virtual pathfinding problem. You want to efficiently and virtually find the shortest path.
Right. And that, I think, is kind of crucial. That's sort of efficient, because that's like dramatic.
Oh, I know. I mean, but that's why theorem proving methods, although there is this frustration with theorem proving that, okay, in this proof, okay, in the end, we will prove a tautology here. The structure of these proofs is you feed in the hypotheses and the axioms, and you eventually transform those two into a tautology, which is not the way round that you would do a standard pure pathfinding, right? Like if I'm trying to prove in this axiom system here, if I'm trying to prove that AB is equal to BAA, I want to just find a straight path from one to the other. But in traditional theorem proving, for reasons I'm still not completely clear on, and maybe somebody here can tell me, you know, what traditional theorem proving does. Well, I mean, essentially what it's trying to do is it's trying to find a path to something, and it's easier to find a path to a tautology than it is to find a path to an arbitrarily specified object. That seems to be the point. Anybody fill that in and explain? I mean, is that a story of why the, you know, that completion algorithms are optimized for finding a way to get to a tautology, basically?
Well, Nick has a nice explanation of this.
Yeah, I think so, yeah. Not all of them doing that kind of proof. Some of them like do refutation proof when they try to prove basically your given negation of your hypothesis
Okay.
prove something like any contradiction.
So wait a second.
Then-
You're saying some theorem provers do that, and some do the thing that we're seeing of proving a tautology. Is that what you're
Yeah.
saying?
Yes, some of them are also like use model theory to improve the search and so on. There are many strategies basically.
Well, can we enumerate these a little bit? Because this is, I mean, yeah, I mean, okay, but you're saying, well, okay, is there any standard strategy that actually gets whose destiny, where it's finding a path from BBB to BAA and so on? Or do they all involve introducing, do they all have logic assumed, basically?
Well, most of them, I think. I'm not sure. Maybe there is. The most efficient certainly have logic assumed and try to do refutation proof or this tautology proof thing.
Right. Okay, so I mean, when we're talking about wherever we listed it, so you're saying automated theorem proving has assumes logic, proves tautologies / refutations, and then there's the additional thing of use model theory as a speed up. And presumably there are other speed ups as well. And the things that I think Xerxes was looking at with Jonathan and so on was this proof to proof transformation. You want to say anything about that? Xerxes is here.
I'm here, yeah. But at that point, we were kind of just using very generic category theory ideas. We weren't necessarily projecting onto some model, but indeed, you could, the model theory side would be basically the semantics of what we were doing.
But so the concept, though, would be take a proof like this and then imagine in a sort of higher category fashion that you can transform this proof, this path in quotes, into another path.
Right.
And that's yet a different methodology. I mean, did you have practical examples of that?
No, we didn't really go into any practical examples. We were just trying to point out the generic methodology from the homotopy type point of view. But
okay. All right. Well, anyway, so look, I just wanted to review for a second for people, this is the basic states graph. Okay, people understand. I mean, I'm going to pick on other people like Ian, for example. Do you understand what's going on here?
Yep.
Okay. All right. So then we've got the concept of let me give you another concept, the concept of branchial graph. Okay, that is the graph of common ancestry. Now, this generalizes to a branchial hypergraph, and I guess Nick is using this idea of not a single foliation, a single layer branchial graph, but the set of all ancestral relationships in the whole multi-way graph. Is that right, Nick?
Yeah, right. If you have a foliation, then you can produce like branchial graph for each layer or pair of layers. But if you don't, you may as well just combine them. That would represent like some kind of branchial graph for all the foliations possible.
But so your branchial graph function, for instance, is if I just take this whole graph, I can feed it, and this is an example of a type of operation, right? I can feed it this thing, and it will just give me this, which is, so that's the complete branchial graph for ancestral relationship between all elements here. Is that correct? I mean, there was no foliation done here. I simply look at two elements here, and I ask, do they have a common ancestor? Is that right?
Yeah, and those weakly components are maybe in this case at least represent those squares. Like
Right,
one of the
but-
components is that graph above.
Indeed, but that won't in general be true. That's a specific feature of this particular rule, I suspect.
Yeah, probably.
Okay, so I mean, this
So
is an
so
example.
You're referring to an immediate ancestor, right?
Yes, in this case. Right. I mean, you could have a multi-level branch hill graph, but that's going to give a hypergraph, not an ordinary graph. Because, well, I mean, you could make an ordinary graph. Why can't you just say join as a graph things which have a common ancestor, at most 2 steps in the past? Why doesn't that just...
It's the same as getting a hypergraph and then converting it to a graph. There's just multiple ways you can do it.
Where the hypergraph is because you can have in general, when you go why do you need a hypergraph when you go 2 steps back? So let's take BBA, for example. What's the hypergraph that connects these things here based on their common ancestry in BBA?
Well, I think you have to take your sink vertex. That would be the first element in the hyperedge. And then you just step back, go backwards into your ancestry, right? And just produce a hyperedge this way.
I'm not... Could you say that again? I don't quite understand that.
Well,
So
if you open the branch of hypergraph resource function documentation, there's a simple example there.
Oh yeah, I've seen this example before.
Yeah, yeah.
Are we able to do that? If I just did this thing for a few steps, let me just make one of these. Okay, so now if I say branch hill hypergraph of this, what does that mean? Is that, maybe I should run another couple of steps. Okay, but these are all graph elements, is that not correct?
Yeah.
In this case.
Yeah, this is just edges.
These things here are just edges. So if I just say graph of rule that's what I'm getting. But so what would it take to have a hypergraph in here?
I guess this time-like path, like in the first example.
A, B, C, D. I see. It's something related to the fact that there is a time-like element there. I'm not completely getting it. But anyway, the real point here is to just say that there are these different kinds of graphs. So this is the states graph. There is a
Is it the case that the branchial graph, that the edges are edges between siblings? And so then you
yes,
could envision having edges between first cousins or edges between second cousins.
exactly so.
That's what you mean?
Yes,
Okay.
that's what we mean. So for example, you can presumably make a branchial graph for a tree. And what is the branchial graph for a tree? It's a let's see, if we pick a okay, so there's a random tree. So now presumably what we would do here is we would say tree graph of that. And now we would say branchial graph of this.
Won't you just have some fragments? Yeah.
Right, because each one of those is each fragment there
Is a set of siblings.
Right. Why is there a? Oh, I see. This like that cluster there. I'm a little confused. So those two will be connected by an edge.
Mm-hmm.
And then, well, like this thing here is this complete graph, right?
Right.
Or,
I imagine so.
Those 4 leaves together. Yeah.
Yes, I imagine so.
But also the 4 children at level 1.
yes. Right. Right. But have you seen this? I mean, in terms of treeology, have you seen such graphs being made? Or Roger, have you seen these for any other purpose? These kinds of
No.
things?
What do you use them for? I mean, I don't get it. Why do you want them?
They're maps of quantum entanglements. I mean, they are, because we believe that, because the whole point is, we think that the different paths here are actually paths of history.
No, I got it. Okay, but
They have other
I was
applications
thinking of
too,
it.
though.
I would like it entangled in something else than that.
You mean in a different field?
Yes.
Well, I mean, for
applications.
example, I was looking at this for games.
Okay.
Okay, so this represents the possible configurations of a game at a certain step, and this is essentially saying, okay, another application is in metamathematics. We're asking, how do you lay out all the theorems? You're generating theorems from a particular axiomatic theory, and you've got them all. They were generated in some way of applying axioms and so on. How are the theorems related to each other? That's a place where the branch-hill graph, in a sense, is a way of reconstructing the space of theorems. Did that make sense?
Maybe.
Right. It's kind of like, because two theorems are nearby if they have a common ancestor.
I see. Yeah.
Is it worth showing an example, like with a token event graph? Branch-hill graph?
Of what? Which one?
We just use a token event graph to show how we use it in metamathematics. And you could take
Well, here's one
graph.
I just happen to have on my screen.
Well, okay, it might not be the most edifying, but okay.
That's one for Boolean algebra. It's a piece of Boolean algebra. And that is actually, that's the multi-way graph. And there probably is, well, we can then make the branch-hill graph from this.
Hold on. So for trees, everything has, everything is connected because everything has a common ancestor.
Eventually, yes. The question, these are one level. Okay, the generic branch-hill graph that we're using is a one-level branch-hill graph. So everything has the question is which things are connected in one step common ancestry.
So you share a parent. Okay.
Yes.
Your siblings.
Indeed.
Yeah, I think it's 0th cousins, 1st cousins, 2nd cousins as you go up further.
Right.
Yeah.
Yes, that's a good. Actually, we could have called it cousin. We should use
like
that.
the cousin graph of a DAG.
Right. The
sibling graph of a DAG.
Which? Say that again.
Sibling graph.
Oh yeah, right. Is that a thing? A sibling graph? Is that a thing?
At least for a DAG, it could be defined.
No, I understand, but it's not a well-known thing. All right. So anyway, so these different. Okay. There's also this notion of a token event graph. So this version of a multi-way system has the property. These are events. That has the property that you start with one state and you can get multiple states from it. In the general case, you can also have something where you have multiple states that are being picked up, or multiple tokens that are being picked up. These states can have multiple tokens in them. So, for example, what is a good example of this where we can?
I mean, the string is almost like that. If you think of them as each letter being a token.
Yeah, that's correct. But we can have a more general token event graph. Well, here was it. Let's pick up the where is it? Okay, so these are token. Okay, these are token event graphs where a single token is turning to n+1, n+2. There's got to be ones. There's got to be an example here where it's not just a single token. I mean, we could clearly do one here where, so this. Okay, that's just single tokens. But now, what's a good example of two tokens? So we could say nm goes to n+m, I don't know, abs of n-m. Okay, so what that should do, let's see, we're starting off from, let's start off from the state 1, 1. It's rather boring, but let's say. Okay, so what's happening here, at every event, two tokens are being picked up and combined in the event, which is then emitting two other tokens. Does that make sense? And in the case of a string, we can think of each event is taking a subpart of the string, wherever we had that up here. It's taking a subpart of the string as indicated like this and doing something to it. So we could as well represent this as a token event graph where the individual tokens are just elements of the string. There's an additional weird constraint in the string that the tokens occur sequentially in some way. But again, we could just pick up individual two tokens here, and they will turn into, in this case, BB goes to A. Two tokens will turn into one in that case. Does that make sense to people? So, in other words, there's tokens. States are made of tokens, and that's where in our multi-way graph formalism, the that's what is it? The state? I forget what this thing's called.
How do you get the graph without the events?
You can use remove events.
Yeah, but we don't have a great way to do that. We don't have a great way to do that. I mean, this particular one here,
there wasn't like already a name for this graph.
No, because we've studied a lot the graph with states. If we think of this as being a multi-way graph on integers, then the integers are the states. Okay, but when we do this with hypergraphs, for example, the tokens are the hyperedges and the states are the hypergraphs. And so the token event graph for hyperedges, for hypergraphs, I think Nick had an example here. Yeah, so this is oh wow, that's cool. Okay, so that's one of our sort of physics project type things where it says this is a hypergraph where we're picking up pairs of hyperedges that have that relationship, and we're creating new. So I mean, for example, I'm sure if we just do two steps here. Oops, what happened? 3 steps. Something seems to have gone wrong here. Did I do this wrong? Nick, there seems to be a problem here.
I see.
Can I try restating what you just said to see if I understand?
Yes.
So the tokens are the vertices in the hyperedges, and the states are like a complete hyperedge.
No, that's not correct. Okay, so the tokens are hyperedges, and the states are hypergraphs. Okay, and the atoms are yet a different kind of construct. They are elements in our physics/metamath project. We're calling them EAMs. They're the sort of lowest, they're atoms of existence, so to speak. And let me see if I can find a good example here. Let's see. Oh gosh, these are incomprehensible. Here's an example. Okay, So this is a multi-way graph based on complete hypergraphs, right? So the hypergraphs are the states here, and every transition represents some update on that state, producing another hypergraph, and the states are hypergraphs. We could fragment this
I see. That makes sense.
into a token event graph by saying, let's just look at the individual hyperedges here, which is much more efficient because, for example, those three graphs share many hyperedges. Okay. The disadvantage is that if you fragment the thing into hyperedges, you've got this big mass of tokens, but you don't know how the tokens are arranged into states. That makes sense?
I think so.
Okay. I think we're now ready to look at Nick's function. Unless anybody has any further. I mean, the main point I'm making is that there are lots of these graphs that seem very natural, that occur in lots of different places. I mean, we could also describe how these relate to Petri nets. That's yet a separate issue of, so a Petri net is something very much like this, except that it is I think Jonathan's calling them capacitated multi-way graphs, where you are using up, Petri nets call them tokens, but we have to call them something different. Where as you, let's see, maybe there's an example here. Anybody else want to fill in what the story is there? Nick, did you understand the Petri net story?
Well,
If they're normal Petri nets, I can explain that. So you have tokens, and you can make a transition. You have transition nodes and you have nodes. And when you make a transition, that token moves through the transition to the nodes on the other side.
A bit like this.
Yes. So those squares look like transitions and those round things look like nodes.
Mm-hmm.
And the black things look like tokens.
Right. Right. Anyway, it's another connection here. Okay, let's look at Nick's thing, okay, which is now multi-replace. Where is it? Here we go. Okay. So, I mean, again, the main point of all of this is how do we unify all these different things? We've got a bunch of functions that do, a bunch of related things. How do we unify all of this? Okay, let's look at multi-replace. Nick, would you like to give us a tour of multi-replace?
sure. The goal is like to combine all those replace functions when you're not certain where you want the replacement to happen and how, right?
Mm-hmm.
So it just provides you the list of all possible replacements, and it works for tuples, subsets, and when it's not just a list but actual different positions on your expression. So you can act as a tuple replacement, subset replacement at different position of your expressions. And you can splice your result back.
Isn't there like a similar function called, we added it not too long ago. It's not replace all, it's all.
Sequence replace. Replace
No,
list.
replace list. Yeah.
Yes,
Yeah.
right, exactly. So replace list, let's look at the difference here because this is relevant, okay? So let's say we say x blank blank, y blank blank, arrow, f of x, f of y.
I have an example there. It's like in relations.
Okay. Okay, so that's what that does. But one thing it doesn't do is it doesn't tell you what it did.
Exactly. Yes. And Nix seems to do that.
Right. Okay, so Nick is showing us here. Let's look at this for a second. Okay, so you say that's the replace list version, and that's now your version here. What the heck did this do?
Right, is that it's not just like picks the position. Like if your first replace list acted only at the root position. But you could also like try the same operation on the position 2. That's why there are 2 elements there.
Okay, but if I try this case that I was doing up here, so oh my gosh, what the heck is this? What is this?
Maybe try level 1. Just
Try with like range 3 or something.
Is that the right level specification? Oh my gosh, does it have a heads option?
yes, heads false.
Okay, what the heck did this do? So why did it give so many more cases than replace list? What is it doing that replace list isn't doing?
It considers all the possible. Also tuple. Oh, well, in this case, it also like your left-hand side, right? List of X and Y. It
Mhm.
tries to find the positions for independently for X and Y there.
I see. So it doesn't, because it is icy, because it's keeping track of what the replacements were, it cares whether X is bound to something or Y is bound to something. Is that correct?
Yeah.
So I see. So that, okay. So again, this is what happens if you trace more. Okay, so maybe we need to try an even simpler case. And it's taking its time. Okay, so 1-1 means that I don't understand. How could it get a single F here? I don't understand. This says X blank, Y blank is this.
Well, that's how it works. X and Y, in this case, are both at the first position. So it only can insert
Oh,
splice.
because it's assuming that this is a subsequence. It's assuming the list is a sequence. It's assuming that a list is a flat object.
It's assuming it's like a tuple.
By which you mean that the list is effectively flat. So
Is
that
it
you can
deleting
put a
duplicates?
subset.
Like it's like F of 1, F of 1, 2, 3, but you don't have both F of 1s.
No, it's binding both X and Y. No, actually, I'm totally confused. I don't understand that first transformation.
Because some of them have 2 Fs and some have 1.
Yes. What is that first transformation? Is that okay? What could I do on range of 3? What replace at could I do on range of 3 to get me that first thing? That first result. Is it true? Wait a minute, we don't have, I mean replace part. Or map at, rather. Is there a map at of replace that will give me that first transformation?
Oh yeah, you just ignore the last.
Do the list one.
Your output contains 2 elements. You just ignore the last one.
I'm confused. So if I take this and I say replace that, and I take the replacement, is this completely wrong what I'm about to do?
It's going to apply it. You just want to do X blank goes to F of X.
Yeah.
But why do I do what? Why is that related to this? Why is that doing the same? Go ahead.
This is like an option. I've decided as default it acts on a tuples, so you can multiply each of your sub expressions as many times as you like. because you specified your left-hand side with 2 elements. So you're asking for all of the sub-expressions at least up to 2 times, including like a single ones. So it gets multiplied. So you just
we had a name for that option. What is it?
You just have subsets true, then it's gonna ignore those cases.
Okay, has subsets. So this is saying, for example, in my, in the token event graph up here, there's the question of whether, if in this case here, could it pick up? So let's say that my initial condition is just 1 here.
Yeah.
Will the something simply not fire? Do we have an option to token event graph that makes it fire in this case?
Can you update your, I think you have a node token event graph. Can you resource update it? It should be 1.1.2 version. That's why your above example didn't work. The hyper edges.
One, 1, 2.
Okay.
I see. So what that's doing there is it's picking up that token more than once.
Yeah.
Okay. Okay, but so the basic idea here, explain, okay, so multi-replace is producing this thing, which has a list of, for each, so how does it know that one of these is X and one of them is Y? This is the part number of the binding for the first variable, is that correct?
Yeah, this is in the order you specified it. So the first one would be always X, and the second one Y.
Okay, but so then in some sense, what we might be doing here, unfortunately, I mean, this is, again, it's a thing we haven't done with patterns, right? We don't have a mechanism. We don't have a function that specifies pattern bindings as such. In other words, if you say, given, in this case here, given that this, is matching against, I don't know what, 1, 2, 3, 4, then we don't have a way of saying X is, in this case, probably the sequence, 1, 2 or something.
Can't you just say X : pattern sequence 1, 2?
What are you saying? X :
pattern sequence of 1, 2.
Oh.
Isn't this like subset replace?
No, but what Christopher is implying is something very interesting, which is that we can treat colon like an equation. I hadn't thought of that. So what you're saying is, if I say f of x blank, and I want to match that, that's a very good idea. And I'm saying, let's say it's match list or something. And we say match this against f of 6. What you're saying is that could return this as a representation of that match.
Well, that wasn't what I was saying, but sure, maybe it could.
That's very interesting, because I mean, then Nick could return here something much less obscure. He could return something that says X. Well, it's actually, again, a little obscure.
I mean, if you have variables and values for them, though, I think rules are much more standard.
Yeah, so I usually like it as an association. This is what my unifiers usually produce. When my keys of an association are just pattern variables. That's why it's very convenient, because you don't have to wrap those patterns with verbatim. You can act with those associations as for replace all, for example, and they can actually replace your patterns as verbatim.
Can you give an example?
Well, try, like, if you have a f of x blank, and try to replace the x blank verbatim with something, right?
No, I'm asking how do you want to do it? Yeah. If I say verbatim of x blank goes to something else.
That's one way to do it. Or you just can make an association when you have x blank as your key. That also works. So that's how I represent substitutions usually for variables.
So you're saying, if I say that, what's the idea? Are you saying that I can then say something like f of x blank slash dot this? Does that work?
Yeah.
Oh, that's something which might have been thought to be a bug, but it's actually a feature.
Yeah. That's kind of amusing one.
Right. Okay. So what you're saying is, because this comes into the category of knowing what you did. And so what you're saying is you have a way to represent the bindings of pattern variables. Now we also need a way to know, when you're doing evaluation, what part of the expression, in addition to the binding of the pattern variables, which part of the expression did those pattern variables come from? Which is what you're doing here. Is that correct?
Yeah. Right.
I mean, it's worth remembering that when we do find equational proof, that it has this very grotesque, in a sense, way to, I mean, it did the best it could, so to speak, as a way to, let's look at a random proof object here. I'll get a slightly more complicated example. Where's a more complicated example? Help. Give me a more complicated example. Oh, for goodness sake. We should fix these examples. These are ridiculously overcomplicated. Ridiculously overcomplicated.
Yeah.
Okay,
Well,
in any case,
yeah.
the point that I'm making is, oh my gosh. Okay, there's one that's at least somewhat smaller. And by the way, also, this should use, oh, whatever. That is a misfeature, the fact that it doesn't, okay, this is kind of grotesque. Oops. Okay, so let's look at this. Okay, so the issue here is we've got all of this construct orientation, and then it's specifying where, I mean, all this stuff, right? So Nick, do you feel that you have a cleaner version of how to do this? In your world, what would these steps in the equational theorem prover look like?
Yeah, like critical polylemma, it's like by substitution. It also requires just orientation and the position.
But so do you have an example? Can you show an example of where you're doing that? You have your function for by substitution, right?
Well, multi-replace also have a method now.
Okay, well, let me see it. So what can you show an example?
From the multi-replace documentation, you can try to find one. Maybe in options method.
Okay. So I want to, for other people's benefit, I mean, this took me a long time to understand. Nick figured out, okay, so substitution. Everybody understands substitution. You take something like, let's look at a specific example. How do we make this be less long? Okay, so this is going to be substitution. That is f of y blank b goes to c. What is the one doing?
Level one.
Okay, so this is now saying f of y blank and b, which is matching this, goes to C. Why did it not match this? Oh,
There's no
because
B.
yeah, there's no B there. Okay, now this is to be compared to co-substitution. In which it can, oh, I'm now so confused about what's happening here.
Nick.
Well, now you can do the unification only at the second position. Now you do it in the other direction. Unify X blank with B. And your Y blank is matching verbatim.
Right. So in this role here, we're dealing with something which we've never really had before, which is things like f of x blank, y blank, and then we've got a rule. Is it a two-way rule or what? Does it not need to be a two-way rule?
No, just a regular rule. It's just the.
But it can have a pattern. It can have patterns on the right-hand side.
Yeah, that's the point. Yep.
And so what we're doing is we're saying we can match both from left to right, where we would normally have, we match the name. So in a sense, a rule that, okay, if there are no blanks on the right-hand side, it's still the case that co-substitution can do different things from substitution. Is that a true statement? Even if there are no blanks on the right-hand side, yes, because what you're saying is you're matching.
It's going to be less than substitution.
We didn't in this case. In this case, it matched the X blank against the B.
Yeah.
Correct? So it unified. What it did was, normally, the rule of pattern matching is you take the thing you're matching to, and you see whether the expression matches that. In the case of co-substitution, you're able to take the thing that you are matching, which is itself a pattern, and you can instantiate part of that pattern to match it with the thing that you are, the rule you're going to apply. Does that make sense, Roger? Others, are you understanding this? What's going on here?
You should also notice that at the third position, X is changed because of this unification.
Right, because X blank was bound to B by, in order to make this a plausible match, you had to do the matching on the thing you were, how do you, I mean, this is such an obscure area. You know, it really needs better names for things. I mean, I think the term co-substitution is actually a good name. Go ahead.
Isn't it unified at two terms? So you have f of a comma x blank and f of y blank comma b, and you want to unify.
Yes, that's right.
Because that's not what we call match in the normal sense, right? Or maybe we want to generalize what match is.
I'm not sure, right? I'm not sure we do. So, I mean, maybe we need, do you have a function, sort of a unification of f of a blank, a x blank, f of, I mean, this seems like it's the core operation here. These two things, unify those.
So
go ahead.
Roman has written several such things over the years. We don't have one. I don't know of a place where we use this right now, but.
Right, we should contact Roman about that. Yeah. He's probably got it in his books, actually.
Yeah, probably, but I can't remember. I think he wrote sort of TMJ articles about it and other things.
Well, let's look it up. Okay, but so Nick, do you have?
Yeah, I have this.
Does it have a name that we could actually use it?
Well, I just called it unify.
Okay.
It's inside of the definition somewhere. It's not. Maybe it's in your mathematics. Yeah, I have it.
Should I specify it differently?
Yeah, I think you should reverse it. Your arguments. I have a unifier, which is like acts as a most general unifier that goes in both directions.
Why does this say message by meters?
I have no
That's
idea.
really weird. I probably substituted somewhere. That's probably where the pattern matching happened, was inside the message. Anyway, so okay, so this should have worked, and it would have then told me that. What would it have told me? That y blank is, I don't know how would it specify the answer?
As
So you have
this
all the things
association.
that, right, but all the things that can be variables, right, which we use blanks for, right, are the things that need a value, a substitution.
Yes, that's correct. Which could be with another variable.
Right, I guess.
Yes, that's important, because even in this example here, weren't we binding
Isn't that for ordinary substitution, you bind named patterns on the right, and for co-substitution, you bind them on the left, and unify is like doing both?
something like that is correct, I think. I mean, the term we're now using for the two-way thing is by substitution. My God, this is obscure. But by substitution is what is needed to get things like critical pair lemmas in automated theorem proving. Is that a fair statement?
Yes.
It's like substitution is ordinary match Q. Co-substitution is like match Q, but you pay attention to the patterns on the left. And by substitution is a match Q where you pay attention to patterns in both arguments.
Yes, but apparently it's more than that. There are cases where are more than just the kind of both way things. But I mean,
No,
so go ahead.
It is both ways. It is both ways.
No, I understand, but aren't there things where if you are doing that on a complicated expression, there is one part of it can be going left and the other part of it can be going right?
Oh yeah, basically this example, are you looking at the third position? That's how it happens, because one of the arguments goes one way, another one goes another way.
Okay.
That's the point. Like substitution plus co-substitution doesn't equal by substitution.
Okay. Okay, but so what we're trying to understand here, I mean, okay. Let's look at some objectives. So first of all, Nick, do you think that you have, if you were designing proof data set today with what we now know about by substitution and so on, what would you write for all of this stuff?
Yeah, I have an idea. I have a function that actually makes a proof object like this from the token event graph.
Which is different from your proof object to, no, you've got proof object to token event graph, but you say you've also got token event graph to proof object.
Yeah, well, a specific token event graph, which is the result of our, how it's called, a cumulative token event graph, when you have statements as your tokens. If you produce a cumulative token event graph with statements, you can make a proof object. When I populate all of those fields, but my way, some of them are kind of dummy results just to make it consistent.
Okay, but one of the important things is that you know, for example, this thing is not readily applicable. And so you've got a version of this, which is a more computable way of specifying what transformation to make and where. Is that right?
Well, more computable, all you need is just like a position. That's what all your keys are in multi-replace, for example. That's all you need in order to reproduce your result.
Don't you need to know like the orientation and so on?
Well, that's if you have a two-way rule, sure.
Okay. But so you're saying that a proof could just be a series of replace parts, or map-ats rather, replace parts basically.
Yeah, just that this is some kind of buy replace parts, replace adds, because you have to unify both way at some position. And then substitute it into whole expression to make sense of it.
Okay, so you're saying there, because this is another issue, is the plugging in. So what we're trying to do here, we've got these various moving parts. We make a substitution, we make a transformation. The transformation is embedded within a bigger environment, and it has to be replumbed back into the bigger environment after the transformation has occurred. That's one thing. And the other thing is there might be multiple transformations which could occur. Is that a fair? I mean, and what we're trying to do is represent I mean, and then we're trying to figure out for those things, what is the result we're trying to, I mean, so for example, with multi-replace, can you imagine that there's a find multi-replace path? Is that the concept that you would, let's say we're trying to get, we're trying to do theorem proving. Is theorem proving basically find multi-replace path?
Exactly, yeah. The find replace path function is just a series of by substitution in some way.
Right, but the thing is that, I mean, okay, so find replace path, but the whole point is that one of the issues that we had in find replace path, I think I have a version of that, maybe other people have versions of it now too. Like, I'm not sure if this is the which version or anything this is, but wow, what the heck is that? Now I'm totally confused. Okay, I'm totally confused by what's here.
No, some working material.
Okay, fine. But I mean, the find replace path that I had in mind was something where, okay, so the version that I had at one point had different things it could return. It could return the pure path, but does it return just the path, or also how the steps were taken in the path? Okay, so in a sense, okay, so find replace path. Okay, what is replace repeated? Isn't find replace path is related to replace repeated more so than to replace. So replace repeated is like a single path, a single virtual, single path that figures out for itself where it's going. So the point about find replace path is you specify an endpoint in find replace path. The different kind of computation that is more like our usual computation is a find replace path with no endpoint specified. Because that's the case where you're just generating a multi-way graph. And, so find replace path is the case. Okay, so find replace path, you know the endpoint, the start and end. You want to find how to get there. And multi-way system is more like, the start. You generate a structure. Okay, there's an intermediate case here, which would be find let's see, find replace best or something. You have a criterion and you want to find the best endpoint you can subject to that criterion. I mean, that's the intermediate case, right? The find replace path, you've pinned the two ends. Find replace, what's the right name for this? I don't know. Find
Maybe find replace best is an option to find replace path. Like, what are you optimizing for?
No, that's a different thing. Okay, so there's a thing here. You can pick different paths, you know, optimizing for different things in the path. E.g. path length, e.g., you know, e.g. size of intermediate expressions or anything, right? But this is a different thing. This is, you don't know where you're going. So this would be things like, you know, find, what's a good example of this? It's like a, you know, like a game where you say, find, you know, find the closest packing. Is that a good example? I don't know. Find the best config, the closest packed configuration. Well, you have many paths you can go. I mean, that's more like these various reinforcement learning-ish type things. It's more like active classification. How does this relate to active classification? Anybody? Christopher, Roger, anybody? I mean, what? You know, because active classification is basically saying you make moves from one place to another. See what I'm saying? I mean, maybe this isn't, it's not quite the same thing, but it's related, isn't it? Have I lost everybody here? Or is this not making any sense?
Find replace best seems related to beam search.
Oh yeah, it might be. And I had actually, somebody had, whose was this? Oh, this is machine learning people have a beam search. Okay, let's review beam search for a second. Okay, is this the quintessential beam search picture? Oh my gosh, this is yet another thing, isn't it? I mean, so.
My understanding is that this is like a breadth first search where you have control while you're doing it so that you're trying to find the optimal path for something rather than just going through the whole tree.
But what is your objective? Or you don't know what the endpoint is going to be.
You're trying to get to that one endpoint.
No, but do you know the endpoint?
No.
I think you
Finding
only
an
have
endpoint.
probabilities. You just follow probabilities. Maybe sample your each step.
Okay. But so what's a typical use case for this? This is used in, I mean, I know it's used in natural language processing, but I'm not sure. Yeah, different people we should have had in this meeting. Okay. Okay, so this is related again to beam search. Okay, but so, you know, what we're understanding is that Nick is providing the low level kind of, okay, so here's a question. What your function is pure structure, looks only at structure. That is, if I had an arithmetic operation going to the right-hand side here, that is not something you can deal with. Because to be able to deal with that, you would have to be able to do things like invert that operation, if I'm understanding correctly. To do unification, you'd have to be able to do that.
Yeah, well, yeah. It's also just inert expressions.
So inert expressions, right. Deals with structural transformations on inert expressions, which is already very useful. But my question is, okay, so again, we could write the whole of our language in principle doing that, thinking about ourselves as doing that. But in fact, we have all kinds of actual computational operations. And is it the case that, I mean, how should we relate these things? In the case of multi-way graphs, it's not difficult to have a multi-way graph where, oh, I don't know, like for example, if I do a token event graph, actually, if I just do a multi-way graph, see, this is a hope. No, let's not do this. Let's do, okay, so nest graph is deeply related to multi-way graphs. Yet another connection that we haven't really brought out here. So if I say nest graph of, what am I doing? I'm saying like x blank goes to divisors of x. I say, actually, what I want to do is I just want to say x goes to, is this right? Divisors of x. And then I say, starting from like 6, going 5 steps. Yes, that's already doing that. Okay, so nest graph, again, is yet another function deeply related to all of this, except that nest graph, which we should have put up at the top here, nest graph, again, doesn't record what it's doing. Am I making sense?
Yeah. Nest graph tagged can record. Right.
So, okay, so it's the, which again relates. So nest graph is, can make a multi-way graph, but doesn't tag things correctly. But by the way, it's worth realizing that nest graph is a super convenient way to make a multi-way graph. The other thing it doesn't do is it doesn't, plus it can't make token event graphs because it's always got one input. Right, so anyway, down here. All right, so you say, if we say tagged, if we have the resource function tagged token event graph, what is it called?
Nest graph.
Nest graph.
Tagged from the end.
I'm not sure we're going to see anything different here, are we? Oh, we are. It's different colors. Okay, so what is that graph, in fact, inside? Has that graph got tagged edges? Is that how it works?
Yeah, you can make tags yourselves. If your output is a rule, it basically indicates your custom tag. By default, it's just an index of your results, right? Because you have multiple divisors, it's just an index.
Okay, for each, so you're saying at each step, it's the index number, the tag is the index number of that edge in all the edges produced at that step.
Yeah.
But okay, so what this doesn't do is to capture, let's see, this is taking a whole function. It's applying this whole function, x goes to whatever you have, as opposed to your multi-replace thing, which is going in and finding a place to do the replacement, as opposed to gulping the whole thing and just producing an output. Multi-replace is going in and finding places that match. So there seem to be these two different, I mean, just as we have in the main system, we've got two different ways to take inputs. One is by applying functions and the other is by applying rules. I think. So in the case of applying a function, there's no analog of this whole unification business. Is that correct? There might be some weird analog of that with lambdas and bound variables and so on. Is there?
think so, yeah. Function is like a rule when you don't have any conditions on your left-hand side.
Right. So this is, again, an operation that we've never had, is unification can also imagine, actually, we have had this issue, imagine unification with functions. So for example, what that is, for example, even in the very basic case, function x plus 1, is that equal to function y plus 1? Right, and the answer is they're not going to say it's equal, but that will be the analog of saying, is that the analog? I mean, you see, that's like saying x blank equals y blank, which we don't consider to be true right now. Is that right, that those two things are analogous?
Isn't the point that a function is always going to apply? And the reason you have unification for patterns is you're trying to decide if things apply?
They're like partial functions.
Well, we don't have partial functions, do we?
We have rules.
I know, but those are not functions. I mean, we
They
have
almost-
rules, but well, except they're not, we don't treat them. I mean, look, in the case of nest graph, the left-hand side of a nest, the first argument of a nest graph is something of this form, which can apply to anything. We have long discussed the possibility of having functions that have rules and that have patterns in their first argument. In which case, then it's the same thing as replacements. I mean, a pattern, that function is just like replace.
Like an anonymous form of down values, of like a thing with down values almost.
I think that's right. Yeah, that would be right. Yes, an anonymous down value object. Yeah, that's an interesting concept. Christopher, have we run across that? Isn't that something that you've needed in the compiler?
I don't think so. I'm not sure. I haven't really seen much of the down value compilation stuff.
Okay, but I mean, because this is like the right-hand side of a down values. If you say down values of f, you get a structure, and that structure is like an anonymous down value object.
Well, the reason that you don't need it is because you have replace. I usually use replace as my head for this kind of anonymous down value, because
Yes.
it's just the same thing.
Right. But although it has its failure case is a little weird. I mean, it's when it is a partial function, and the partial function. Okay, so what you're saying is if I say replace x blank goes to x plus 1, and I just apply that to something, I'll get that, which is very nice. But now if I say x blank integer and apply this to pi, what? Why did that work?
Didn't do a replacement.
Oh, it didn't do the replacement. Oh.
Which is different than if you like defined f of x blank is x plus 1 and then do f of pi, you get f of pi.
Right. So the bug in this case is if it doesn't do it, the function just evaporates.
Well, but if you look at what down values actually returns, the left-hand sides will include the f.
Yes,
It replaces the whole expression, right? So
I see.
Maybe it would be beneficial to have a version of this when you have a failure case, when the application.
Right, where it doesn't evaluate.
Yeah.
Right.
I mean, the failure case for replace definitely should.
No, I know.
Like,
should there be a
yeah.
version where the failure case does not evaluate? But what you're saying is that down values, if I define, well, you're saying that the analog of the down values thing would really be f of x blank integer, or just f of x blank goes to x plus 1, and then I apply that to g of x, g of 7.
Wait, you mean f of 7?
No, I meant g of 7, because then it doesn't do anything. And that's the exact analog of what down values does, which is...
Sure, or if you said f underscore integer, or f of x underscore integer, and then you said f of 7.2, then you'd get back f of 7.2.
Right, which is not bad behavior.
Yeah.
You know, I think I haven't really thought about these things since we made replace have that sub-value, operator form. Because that's pretty nice, that way of thinking about it. I mean, so that is, because we've discussed making essentially lambdas with patterns, and the point that Nick is making is that's completely unnecessary because we basically already have it.
Yeah, I started using it all the time. It's like instead of ifs, I have replaces everywhere.
That's a good idea, but I mean, but should we look at the a failure case where should we look at this? Would that help in the code you write?
Yeah, I think so. So either failure or missing. That would be very helpful.
And then is the idea also that there'd be a function like down values, but it would return, versions where the left-hand sides were somehow transformed. Well, the issue is that, yeah, I mean, I guess the left-hand sides have to be transformed to be some sort of pattern sequence things, right? Because if you take the f away, it might take multiple arguments. I'm not sure what happens if you say, replace if you use the operator form of replace on a sequence, and then the left-hand side of the rule is a pattern sequence.
Okay, so let's say, I mean, this case here, arrow f of xx, let's say, and then we apply that to, I can't imagine this will work.
Maybe it should, though.
Maybe it should work. Maybe this
I'm not sure. Well, I'm not. Yeah, I mean, because it can't work in replace because replace takes other arguments.
Obviously, right. But it certainly could work in the operator form. I think we just didn't think of this. I think this could work.
Is there any way of writing some? I'm just thinking if there's any wrapper. I mean, replace pattern sequence is not right because that's for patterns, not for values that you're replacing. Is there any other wrapper that you could put around the things in the argument slot, the 789, to sort of group them into one thing?
Why do you need to? I'm sorry. Why does that?
I'm not sure you. Well, I'm not sure you do. I'm just wondering. I mean, if there's some we could add support for this sort of taking a sequence in the operator form of replace. But the question is, if you were even using the normal version of replace, is there some way that you could feed it a sequence to replace?
What's interesting, me and Jose, we're thinking about, we don't support vector functions or, like you have functions of matrices and other structures, basically. Sometimes you want it flat, sometimes you want the structure. And so the question is bridging between the two.
Mm-hmm.
And this seems very similar to that problem. Like I want to hold on to it, you know, in some container.
Yes, but then I want the container to melt under certain circumstances.
Yes, exactly.
Well, right, that's the problem. Look, that's the problem of sequence. That's the problem of the thing that was called null projection in SMP. These things that I've always hated because it's like you never know when it's going to melt. And that's what's nice about nothing and splice and so on, is that they're very well defined. They only melt when they're inside a list. I mean, go ahead.
There's like one example I've posted, but very amusing one of when this can go wrong.
What the heck is that?
What?
That seems like a bug.
This is
wait, is X defined somewhere, or where'd the 1 come from?
Let's check. No. Okay, let's try to understand this piece of code. Okay, I'm gonna turn that into of B just so it helps me understand it.
If you get rid of the X colon, well, I didn't even know you could put. I didn't even know
I
you
get
could.
the same thing in a new kernel.
Right, and what's happened here is that it bound the X, even though it had nothing to bind it to.
Well, yeah, I mean, does it ever make sense to bind a pattern variable inside of an except? Like, what does that even mean? Because the whole point is that the thing doesn't match.
Right.
So if you said match anything, except of X X underscore integer, right?
Yep.
Then X could be any integer.
Yeah, so it has no idea what to bind to it.
So so that should be an error. I think that's the problem here.
Nick, do you think it's anything other than a bug?
If you could just return missing or something. If you have a version of replacement, the replacement can happen and return missing or failure, then this is the example when this also should happen.
Well, I don't think it should return a missing. I mean, I think this is a malformed pattern, right? Because it doesn't mean anything
argument
to
would
bind.
Right. What should happen is that the X should turn red inside here, probably.
Yeah, and it should yeah.
Like it doesn't know whether it's red or not until it applies to something.
Doesn't it? I mean,
well, no, it does because it's
I don't think
inside of an accept. I mean, the point is, if you said
it still work inside accept, the problem is that you use it on the right hand side when it's bound inside an accept.
You can perfectly apply it to A there.
The way I would read this is that X is A, and then this should match anything which is not A and be converted into X, which is A. So return A.
Right, but see, this doesn't make sense either because the pattern shouldn't be applying, right? Or no replacement is happening in this case here because the accept failed.
Right. Because
right, so that's what's happening in this case. It's not that it's actually performing a replacement.
Right. So the problem is that match queue. Okay, so here's the problem. There's another problem of this kind, which I remember showed up in 1987 when we were writing. The heck is it? It's the case where. What is it? It's a case where there's an optional. See, the issue is, okay, the question is, can the binding of a variable affect the matching of things? So, for example, if we say match Q A except A, it'll say false. Okay, if we say here except B, it'll say true, right? Now, the question is, let's say we simply add the annotation X colon in here. You would not expect that to affect the matching. The fact that X
well, I might, because again, there's no, like, I think that when you ask for, like, I don't think except, the pattern inside of except is not, like, there is no like, for other patterns, other than except, and maybe there are other similar cases, but almost every other pattern, there's a thing that it sort of clicks onto. But the argument of except doesn't click onto anything, right? It's just saying, it's saying that this doesn't click on anywhere. And so if you say something like X underscore integer in an except, it just means any integer. X is bound to any integer. Like, I don't think it means anything to bind a variable.
No, X is not, but it isn't.
Except.
But it isn't in fact an integer.
You're just saying that the expression doesn't match X bound to an integer.
Right, but then the point is that
X means.
But then the point is that I think if you use X anywhere, right, outside of the except, then it's meaningless. I mean, it is true though that if you use the except in if you use the X a couple of places inside of the except, that should be fine, right? It's just if you then take the X outside of the except, that doesn't make any sense.
Mm-hmm.
But so,
but maybe actually, sorry, one other case. Let me think if this makes sense. What if you have what if you have an X that appears somewhere on the left-hand side of the rule, and then also
Yes,
appears
inside of
somewhere
the-
in the
inside
accept
of
on the
the
left-hand side of the rule? Yeah.
right. And so I think you can get cases where you bind the thing outside, and then the question is there a consistent binding of the X inside? And there can, it can be, yes, there is, no, there isn't. Look, I think there's a thing that should be done with syntax coloring here. I mean, this is
Well,
very
it kind of sounds like the cases where it doesn't work. I mean, it's basically it's a fairly complicated case that you might not be able to catch with the syntax highlighting stuff. I mean, it sounds like, and maybe when you think about this more, it's basically when the only place that you could figure out the value of X is inside of this accept, right? That's the only place where it's bound.
Yeah.
Then it won't work.
This is very reminiscent. There was a bug that was one of our longest running, oldest bugs that is a pattern matching bug that is exactly like this, but it was before we had accept. I'm trying to remember what it is. Does anybody perhaps remember? It's a bug.
Is this the single longest running bug? Although it turned out it was fixed in like version 4 or something.
I think it might have been. Yes, it was a thing. But then no, there was an issue like this where I think we eventually decided to simply not have it match, because it was a case where there was a thing in there, but it couldn't be bound. And the question is, can the inability to bind affect the matching? That's the question. Should the inability to bind affect whether the match can take place? And because that's what it has to do here. Otherwise this thing is going to get tangled up. Well, either that or it has to have a generic, I was unbound, it's either should the inability to bind affect the match, or should it return some kind of unique. Okay, so I'm going to make a claim. Unique UUID'd object. I'm going to make a claim that this is just like an escaped module variable. Do we believe that claim?
By inability, do you mean like you use the same symbol multiple times, but you can't find a consistent binding, or just
no? I mean this case here.
happens?
I mean this case here where it simply doesn't have a thing.
I mean, the point is that most of the time when you bind a variable, with the pattern matcher, it's that you have some input expression, and that and then that variable is sort of clicking on to a piece of that input expression. But with things like accept and maybe some other cases, there is no, you're not asking it to click on to any part of the input expression, and so it's just kind of floating in space.
Right.
I guess the problem is that the pattern matched, but not all of the variables could be filled.
Exactly. But you see, I claim that that's extremely like, a hypergraph rewriting rule where one of the things on the right-hand side didn't appear on the left.
Well, wait, hold on. What happens if you use like alternatives or something like that, and just do this? Say like x underscore integer, or alternative y underscore real, and then replace that with x comma y, and then see what happens.
Funky. All right, let's see what it does. What the
It's
hell?
actually-
This is the behavior of repeated and repeated null, which I use sometimes.
What
Like
is
repeated
it?
null comma 1.
I mean, it's just
when
it's
you
a
want it to
sequence open
match
close.
something
You need
or
hold
nothing.
complete. You need hold complete probably. If anything is going to work at all, you need hold complete, because it's turning into sequence open close. Okay,
Nope.
but it got.
No, this is exactly like what repeated null does.
But repeated null is supposed to. Repeated null is supposed to. it has the option of matching nothing. I mean, it's a triple underscore, right? I mean, the point is with a blank, you expect there to be exactly one thing.
I don't understand this at all. I think this is related to the
I mean, why is being bound to sequence open close is I think what's happening here. But the sequence is being kind of
yeah, it's
somehow
being mysteriously
it's evaporating
resolved.
too quick. Yeah. I mean, hold complete is a sequence hold function, right?
Yes.
But it didn't get it. So
right. So I think it's being replaced out too quickly. Yeah, well, I mean, this is the question of should things see, yeah, this is a good argument for not making things not match when you can't bind things, because otherwise this wouldn't match at all.
Right, but then the question is, in the case with except, does that mean X should be bound to sequence open close?
That's so freaking weird, but perhaps so. I claim that it should actually be bound to a module variable.
I don't think that makes any sense. That's very weird. I mean, you're just thinking about, you know, okay.
I'm thinking about making space in physics, but no, but I'm thinking about, the reason I'm thinking that is that if you have this result, okay, so let me show you an example.
I mean, I think it's both confusing it's neither understandable nor useful, right?
Okay,
I mean, if it returns an unbound module
here's one
variable.
of the problems. Here's one of the problems that we're going to get into. Is that really what we want? And the only way to avoid that, yeah, go ahead.
I think that's kind of like saying, you know, I did plot of 2, you know, equals, like, it's like saying import of some broken string equals import of some other broken string. Both of them return $failed, but it says that they're equal. It's sort of like,
okay, fair enough.
Both of them failed, yes, but actually, maybe just, sorry, one quick thing with the alternatives. Could you try just modifying the thing below to just say arrow Y, just so you can see, don't wrap any, like, just on the right-hand side, just write Y, because then you'll see the sequence open close. There you go.
Magnificent. That's really weird. Okay. I mean,
another way.
I think it's really nice that it doesn't make an explicit sequence, because I use this when I'm passing things into things that may potentially be sequence hold, and I don't want sequences. I just want there to not be anything.
What happens with, like, if you have something matching a triple underscore and you pass it into hold complete? It doesn't have a sequence there, right? Like it evaporates the sequence immediately. It doesn't. The hold complete can't catch the sequence.
yes.
Yeah.
Well, that's, you know, this is the problem. It's like quotes, right? This is, you know, the incredibly high temperature melting of sequence, so to speak.
Another
okay,
argument to have like this sequence to make sense. If you draw parallels between patterns and logic, sequence is like false, where your just blank is like true because everything can match it, and nothing can match sequence, and also except
Except of underscore. I think things can match sequence, like, you know, sequence pattern open close can or pattern sequence open close can match sequence, can't it?
Okay,
or even
for example,
underscore, triple underscore.
If you have alternatives and sequence, right, it just makes it, it's the same as except blank. Empty alternatives is like except blank.
Okay, so your claim is that true is like blank and false is like except blank. But you're also claiming that sequence open close is somehow like false.
Because except blank is like empty alternatives and alternatives of sequence.
Wait, this is a De Morgan's law thing. I mean, where you're saying that if empty alternatives, that matches nothing, and so then the empty and has to match everything or something. But I'm not sure what the and would be.
So your claim is this will match nothing.
Yeah.
I mean,
yeah.
Except
if
I
we're
wonder
following
whether,
that version, if we're following classical logic, then that matches nothing.
Yeah, which is its own.
I think there are other logics where that does match things, but people don't use them very much.
Wait. Does it require law of excluded middle to have that match?
No, it's not law of excluded middle. It's just that there are some logics where basically the existential quantifier over nothing returns true. I think true is the unusual thing for it to return, right?
Yes.
So
we have this problem too in intersection bracket, which represents a whole universe. And so we don't have a representation for that.
Oh, that's interesting.
I think it's fair for it to fit. Does union open close return empty list?
I'm sure it does. Yes, it does.
Wow. Okay.
That's an interesting problem. So I mean, that's similar to. Sorry,
this would be an insane thing to introduce, but you could have something where intersection open close sits unevaluated, but then functions like union. If you do a union of an intersection open close if you do let's say an intersection of intersection open close with like the list 1, 2, then it will just return the list 1, 2 because it treats intersection open close as this symbolic representation of everything. Right. So that seems like a very bad idea. I mean, there's also universal set problems and yeah.
Right. Well, I mean, this is like infinity. This will be the analog of infinity for sets. I mean,
but like it's not even like there's a Russell's paradox maybe, and yeah. I feel like this is very doomed. Member Q always returns true on that object or something.
But it probably happens because intersection is flat.
Oh, if you run into, can you try it, please? Yeah, just
intersection of.
But member Q won't work on it, so that won't.
What did it do? I mean, did it know that intersection?
It's flat. So the first intersection disappeared.
Oh, that's cool. Okay.
But if you used another set, if you used complement with it, then it wouldn't work.
Right. If we said the complement of this with that, it has no way.
You need that to be in the second argument or further. You can't have that in the first argument because the complement is infinite.
Well, no, that's the infinite. That's an infinite set.
No, but I mean, if you ask for the complement of 1, 2, comma everything, then you expect the list 1, 2, but it's not going to work. So which is fine.
Yeah. Okay. We just looking at a couple of comments in our local chat here. Everybody is too used to. We have Richard here, who's joined us for many live streams on the outside world. So, and is used to chat only. But let's see, what was this? Branch or grass depending on foliations. Yeah, well, we don't have a way to specify foliations, guys. I mean, this is the problem. Coming back to this question about evaluation orders, we have traversal order, but we don't have a more general way. In a graph, for breadth first search, all we have is, I mean, we don't have a way to specify what the sequence of anti-chains, so to speak, in our post set should be. There are many choices of possible sequences of anti-chains. Which one do we want to use? And I just don't know any formalism that even talks about that. Does anybody know any formalism that talks about that question? And our physics project doesn't count. But, descriptions of sequences of anti-chains. Is there a category theory way of thinking about that? Anybody?
Xerxes?
Anybody? Okay, blank on that. Richard is commenting about what Unify should do, which was up here where we were talking about Unify. Well, we can put it down at the bottom here.
That example is interesting because you you have to sort of apply until fixed point. The result that I gave as an example, if you apply those to both arguments of Unify, you end up with matching arguments.
So wait a minute, you're claiming this can't be done in one shot. You have to go.
That's right, yeah.
You can try it. It's like I have a function that does this. It's not Unify, but Unifier. Unify just goes in one direction.
Which order should I do these arguments in?
It doesn't matter. Seems right.
So wait a minute, but this is giving a different answer.
Yeah, it's already substituting. It's equivalent, but it's already substituting the y into the z result there. So it should just leave that. Yeah, it's not like minimal, but it's close enough, I think.
But which one is correct? I mean, the y blank. Could the y blank be anything? No, I see the y blank
is j of w blank.
No, I understand, but the y blank could be in Richard's version. The y blank has not been substituted, but here, because you're saying you could have this in a form where you were imagining that this association gets repeatedly applied to determine what happens, which is what Nick has done. Nick has as much as possible resolved this, so to speak.
Yeah, my point is, if you apply this result to both of those expressions, they would produce the same result.
Okay, let's try it. Okay, so you're saying
replace O.
Oh, that's why I should have been doing this. Okay, so then this is this unifier here. Should be that. Okay, oh my gosh. And then you're saying if I take that. Very good. But you're saying, okay, is this like solving an equation? I mean, are there multiple solutions that will work?
I guess so.
So for example, if we had Richard's version here, so let's say we say in this, instead of this, we have y blank here, j of w blank, g of z blank. G of z blank, is that right? Is that what you're?
That's correct, yeah.
Okay, so now we take this, get that, and now we take this. Aha. It's not the same.
Maybe replace repeated, that was the point.
That's correct, yeah. Replace until fixed point, yeah.
And I have to do that here as well. Oh, wow. Oh my gosh. Well, that's interesting. Okay, so is there a well-defined notion of, so is there a well-defined notion of one-shot unifier versus fixed point unifier? In other words, is the one-shot unifier well-defined, or is it something where the only thing we can say is that if we keep doing it, it will always resolve to the same thing? In other words, is this like, a confluence property for term rewriting? I bet it is. I bet the only thing you can say for sure is that yeah. Let's see, Richard had another comment here about iterative deepening A star as a case where revisitation occurs. Oh, wait a minute, is this relevant? Did you just put
Those are separate. Sorry. Yeah.
Okay, those are different.
Yeah, but they're still relevant to our discussion, I think.
By jungle evaluation. What the heck is this? A jungle morphism. That is even a scary concept. What on earth is this? What is a jungle?
Well, in the abstract, they define it as an acyclic hypergraph, represents a set of terms such that common subterms can be shared. So it's this whole sort of term graph subsuming term, story, but it seems to be involved in sort of efficiency of term rewriting systems. Yeah.
Okay.
And this is a tree traversal via attribute grammar story.
What does that mean? So you're saying, where is the attribute grammar living? Does it live? Is it living on the tree? And then you're saying which way to traverse based on content on the tree. Is that the idea? Do we think? I think this is something where it matters what's in the tree, how you traverse it. If I'm not mistaken, isn't that what an attribute grammar does?
Yeah, I think that's what this is doing. Yeah, it's like a controlled evaluate. Yeah, so it's with this sort of dynamic evaluation order question. Yeah.
Right. So this is
attribute grammars are related to treefold.
Yes, I think that's right. Right. So this is determining tree traversal by tree content. Or that was DAGs, actually. Was that DAGs or trees? I can't remember here.
Generalizing from trees to DAGs.
And both papers refer to this, sub-expression sharing aspect.
Right, which is what, that's the main reason people want to use these DAGs, is that like for the combinators thing, sharing, doing combinators with DAGs was dramatically more efficient. Okay. Anyway, what was the comment about A star?
So that was like if you have we speak about computationally bounded observers, but one aspect of that would be, say, memory bounded. So you only have a sort of finite scratch space to think about your states. And so that's a case which occurs in sort of classical search, or search from classical AI, where one wants to sort of find the lowest cost path. And in order to do so, you have to sort of revisit nodes and sort of expand the search tree sort of non-uniformly.
I see what you're saying. So it's like a stack. It's a bit like a stack, having a bounded stack or something with which to. That's an interesting question as well. I mean, that's an interesting observer theory question of bounded computation / memory for observer theory. So one question would be, what kind of recursion can you do with a bounded stack? Because if you're doing depth first search, if I'm not mistaken, right, you have to have an unbounded depth of stack.
Yep. And this is why IDA star was sort of introduced, because it solves that problem of running out of memory, because you keep having to
What is IDA star? What is that?
IDA star is iterative deepening A star. It's a graph traversal path search algorithm, and it's a variant on A star search.
And so that, I see. So that's a thing. and that's probably what that paper was something about the sharing the pain thing. I would guess is something not unrelated to this as well, because it's kind of asking the question, because you have a you have a stack depth. As I hadn't thought about that. I mean, in other words, you have, and this relates also, Ian, to your tree traversal business. In tree traversal, you are, let's see, I mean, you're, if you do breadth first tree traversal, you don't need a deep stack, right? You just have, I'm not wrong, right? You're just doing, it's a very shallow stack. Can we, if we do, is there a way of seeing the stack with
If
tree
you do a
fold?
bottom up breadth first, then that's not the case.
No, if it's bottom up,
The
it
top
won't.
down breadth first, yeah.
Right, but can we see the stack? Is there a way to use tree fold or something to see the stack? In other words, can we, okay, here's an exercise. Given a tree, label every node by the state of the stack when you visited that node.
I could put something together. I don't think it's particularly easy with top level functions.
Okay, it will be interesting to see, because that's I just hadn't thought of this. Okay, so
some of these things involve like multiple like stacks and queues.
what do you mean? So Richard is quoting something here about A* keeps a large queue of unexplored nodes that can quickly fill up memory. IDA* does not remember any node except the ones on the current path. Requires an amount of memory that is only linear in the length of the solution it constructs. Okay. This is a good idea, which had not occurred to me for the whole observer. Yeah, I mean, that really is the question of does the observer know where they are? You know, how much information does the observer have? You know, stack depth is like asking, you know, how much information about their location does the observer keep? So in other words, it's like you know, Theseus and Ariadne and the Minotaur and pieces of string and so on. It's like, does Theseus just remember, was Theseus, wasn't it? I'm thinking only about his ship, but you know, when Theseus is going around the labyrinth, does he remember only, you know, what turns he made, or does he maintain a piece of string that keeps information about what the sequence of turns was? That's perhaps not a useful analogy. Well, okay, we have run out of time here, and actually the meeting that we are doing next, I think, has a rather overlapping set of people, and maybe we should just stay on the same. Well, maybe not. What is the next meeting? It's about expression trees, right?
Yep.
Ian, that's your meeting, right?
Mm-hmm.
Do you have an agenda or something? Did you send it through? Because we could just bring it up here and just see whether it's how overlapping with this it actually is.
I just sent it to you.
Okay, great. Is this not very overlapping, or is it, Ian?
I don't think it touches on anything that we're discussing in multi-computation.
Okay, all right, fine. All right, then we'll make a separate meeting. Okay, well, look, guys, I mean, on this, wow, this is a complicated area. Roger, do you have any wisdom about any of this?
I think Roger already left.
Up. Oh well. Then he's like the except. He's like the bound variable and the except. Okay, and I mean, we will need to continue this. I mean, it's going to take. It looks like, probably what we should try to. I'm still a little bit unclear. There's still many different threads here that need to be pulled together. And Nick seems to have some great functions that are starting to take shape here. And I want to make sure that we understand. So, for example, having the thing that is the future of find equational proof that has a different form of output. That is, where you can take the output from find equational proof and actually sort of execute those transformations. That's clearly useful. And it's seeming to me like we need to have a design where there are on the order of 10 functions that include things like find the branch yield graph of a given graph, find these unifiers, all these kinds of things. We're going to need a bunch of these functions. And we should basically plan on trying to design on the order of that many functions. I'm just not confident yet about how we deal with this. I mean, it really relates to this observer theory, foliations business, etc. Anyway, well, this was interesting, I thought, at least. So thanks to everyone here, and thanks to some comments on our live stream here, and I guess we're going to we'll be live streaming the next meeting as well. But see you all soon.